All right, so let's just write down Newton's first law of motion. An object moves with constant velocity unless acted upon by a force and sort of the result of this is that if an object is moving at a constant velocity, it's going to continue moving at a constant velocity forever, or until a force acts upon it. Remember, in the incorrect laws of motion, he said something differently, right? He said that an object will naturally come to what? Rest. It will eventually stop. And that's what we observe, and that's why we think that happens, because we see things stopped all the time. Like, for example, right now, you're all sitting there and you're stopped because you're at rest now. And if you walk outside, eventually it'll stop. If I kick something across the floor, eventually it'll come to a rest. And so we see that, we observe it all the time. Let's define, so this idea, the idea that an object has this sort of natural state, is an Aristotelian idea. Aristotle believed and taught that objects have a natural state. And really, right up until Newton's, this is why Newton was so groundbreaking, because he took hundreds and hundreds of years of thought about the motion of objects and said, no, that's wrong. Objects don't have a natural state of motion. Objects only have the state that they're currently in. And unless a force acts upon them, they're going to stay in that state of motion. But Aristotle, he sort of believed this natural state of motion, which, by the way, is to be at what? Is to be at rest. It was almost a philosophical or a spiritual or a sort of a metaphysical state, that he sort of saw that when you took something, like if you shot an arrow into the sky, that it was almost a metaphysical thing, that you were violently tearing it from its state of rest and putting it into this motion that it doesn't really want to be at. So it wasn't an entirely physical idea of the way that we think about motion today, but it was physical, but it was also this sort of spiritual and metaphysical idea. So Aristotle believed that objects have this natural state, and then Newton said, no, that's not it at all, that objects don't have a natural state. Whatever state they're in, whatever state of motion, whether they're at rest or they're moving at a constant speed, they're going to stay in that state until a force acts upon them. We need to define net force here. A net force is the sum of all the forces. I'll write this in a couple of different ways as we're going through. I'll either write it as F net, or I'll write it as the sum of all the forces. This is, what letter is this? That's the Greek letter sigma. It also means a summation. So we use it in mathematics as a summation. So it just means the sum of all the forces. So for example, if I have an object, and I have a force, say, of F1 equals to, 10. Our unit, by the way, for force is going to be Newton, so I'm going to write that there. And our F2 over here is equal to, say, 20 newtons. Then my net force is the vector sum of this. It's not going to be 30. It's not going to be 10, but it's going to be what? The vector sum of these. It's going to be negative 10. Right, so remember when we're adding up vectors, this one is in the positive direction, this one is in the negative direction. So when I add them, I would say the sum of the forces equals 10 minus 20, or, F1 minus F2, and then that's going to be negative 10 newtons, or 10 newtons in the negative x direction. That is our net force. Now later we'll do forces in 2 dimensions, and we'll do like we did in chapter 3 where we're adding up vectors in 2 dimensions. and that'll come back. But for now, we can just think of them in one dimension. Okie dokie? All right. Let's try this. So, if an object moves with constant speed, the net force is equal to 0. Is that a true or is that a false statement? If an object moves with constant speed, the net force is equal to 0. Is it true or is it false? Remember, Newton's first law says that an object will stay in its state of motion, whether it's moving or at rest, unless a force acts upon it. So how do we jive that with this statement? Feel free to ask your neighbor. About a third of you have it wrong right now. Just be aware. All right, I'm going to stop at 112. 112. Okay, good. It is it is a true statement that if an object moves with constant speed, right, it's in this current state of motion, which is at a constant speed, it has no net force acting upon it. It has no external force acting upon it. See, those of you that put false, you're thinking Aristotle, that if something's moving at a constant speed, it must have a force acting on it. You're very Aristotelian, you are. It's hard to break away from that. Okay, now Newton's second law. We need to define a couple of things. Hold on, let me go down for just a second. Check something. Stay where you are. Okay, good. Okay, so Newton's second law, it says that the acceleration is proportional to the net force. That if I increase my net force, I increase my acceleration. Now remember the incorrect law of motion. The incorrect said that the velocity is proportional to the force, but that's not true. If I increase my force, I don't just increase my velocity, I increase my acceleration. So the acceleration is proportional to the net force, and it also says that the acceleration is proportional to the inverse of the mass. So if I have a more massive object, it's going to accelerate for a given force. Now we can combine these, and we get that the acceleration is equal to F over m, or as you've probably more commonly seen it, as F equals the mass times the acceleration. These are vector quantities, our force and our acceleration, but mass is a scalar quantity. All right, so that's our Newton's second law. See, I forgot actually to define inertia, so let's go back to the previous slide. And I'm going to define inertia down here. Sorry, you can do it on that page, but it really fits right here. So regarding the first law, this is sometimes called the law of inertia. And inertia is the tendency of an object to continue in its state of motion. That's really just a restating of Newton's first law. And that's why we often call it the law of inertia. Inertia is measured by the mass, or rather mass is a measure of inertia. All right, so if we measure the mass, that is a measure of the inertia. Objects with more mass have a greater tendency to continue in their state of motion. Right? You got a big football player, He's so big, he's hard to stop. He has a lot of inertia. Right? That's a part of the reason they even as far as they're strong, and they need to be strong to play football. But they also have a lot of inertia, and they're hard to stop because they have a lot of mass. All right, so mass is a measure of that inertia. Newton's second law. Newton's first law is often called the law of inertia. Newton's second law is often called the law of acceleration, because it describes this relationship between the acceleration and the force. Let's do a quick problem. These are pretty basic, but they're from the MCAT. I'll pull it up from the MCAT prep. All right, so we want to just work this first problem. It says 1,000 kilogram. Let me zoom in here. 1,000 kilogram rocket ship traveling at 100 meters per second is acted on by an average force of 20 kilonewtons, that's 20,000 newtons, applying in the direction of its motion for 8 seconds. What is the change in velocity of the rocket? So let's try this. I have a force of 20 kilonewtons, so you want to write down everything that you know. We know that the force here is 20 kilonewtons. That's 20,000 newtons. If you like, you can draw a picture. So I have this rocket. That's traveling along. It has a certain mass, 1,000 kilograms. It has a force that's acting upon it of 20,000 newtons. So my force is 20,000 newtons. And then I want to know what is the change in velocity. So after a time of 8 seconds, I'll write this on this big screen in just a second, but after a time of 8 seconds, I want to know now what is the change in velocity of this rocket ship with this certain force acting upon it. All right? Got all the details of this? Can I go back to the original screen so I can write there? I'll wait just a second. Don't bother writing all the words down. Yay. Can I bring this screen back? Okay. So I had a rocket ship. Thousand kilograms. It has a force acting on it, 20,000 newtons. I know that the initial velocity is 100 meters per second. And I know that this force acts for a time of 8 seconds. So it turns on its rocket boosters or whatever for a time of 8 seconds. And I want to know now what is the change in velocity, or I want to know what is my value for the final velocity. All right? So I know what my force is, I know what my mass is, so I can figure out what my acceleration is. A is equal to F over m. That's going to be 20,000 newtons, or 20 kilonewtons, divided by 1,000 kilograms. And so that acceleration is going to be 20 meters per second squared. So for every second, its velocity increases by 20 meters per second. If for every second its velocity increases by 20 meters per second, then it's going to increase by what amount? Well, it's gone for 8 seconds at 20 meters per second squared. It's going to increase by 160 meters per second. If you go back to our equations, our kinematics, it was V equals V naught plus A times T. That's V naught was 100 meters per second. And then our change is going to be 20 meters per second squared times 8 seconds. So that's going to be 100 plus 160. So my new speed is going to be 260 meters per second. You could still see some kinematics problems. In fact, you probably will on this next exam. They won't be quite as complex as the ones that we had on exam 1, but they'll be something like this. What is the new speed? What is the new position given the acceleration that's provided by this particular force? So something along these lines. But you're not going to see the same stuff for this chapter that you've seen before, like in chapter 2. Though in this, yeah, Madeline? For right here? This one. Mass is in kilograms, right? We'll always use kilograms for mass. Good question. Okay, folks? Y'all okay on this? We're just sort of taking Newton's second law and then combining it with some of our kinematic stuff. Okay, let's try this quick test. This one's a little bit more complicated, but remember, our Newton's second law is that sum of the forces equals mass times acceleration. And so here, you're going to want to think about the forces that are involved. I'm going to help you a little bit with it because we haven't gotten to weight yet. But the weight of this force, I have a gravitational force. I'm going to call it FW. It has a mass of 10 kilograms. My weight is going to be 10 kilograms times 10 meters per second squared. And so this object has a weight of 100 newtons. Don't sweat that too much right now. We'll talk about that a little bit later. But the weight of this, you know, we talk about the mass, but the mass and the weight are different. They're related, but they're different. And so the weight of this object is 100 newtons. And what I want to know in this problem is what is the tension in the rope? What is the tension in the rope? I'll go ahead and start this. What you're going to have to think about is the forces that are involved, and then you also need to think about the acceleration. Because notice, in this object, this is an elevator that's accelerating downward at 2 meters per second squared. And so think about how does that affect the tension in the rope when we consider Newton's second law. Okay, many of you have the right answer. About a third of you don't. So feel free to ask your neighbor. See what they put. Please do tell your neighbor what they put, what you put. Let's see, I still have a couple of exams. I have Evan to go and Andrew Barbier. So if y'all are here, drop by, I'll give you your exam afterwards. All right, I'm going to stop at 145. 145. Done pretty well on this. Okay, awesome. C is the right answer. The way you want to do this is you think about, first of all, what is the net force? Our net force is this force minus this force, because one's going up and one's going down. So first of all, on these questions, ask yourself, what is the net force? My net force is Ft, which is positive, minus 100, which is my weight, 100 newtons, equals to the mass. And then you want to think carefully about the acceleration, because here the acceleration is downward, right? So that means that the acceleration is going to be positive or negative? Negative. So my acceleration is minus 2 meters per second squared. See, I'm looking for Ft, so it's going to be 100 newtons minus the mass, which was 10 kilograms times 2. This is 10, minus 20 newtons. So that's equal to 80 newtons. And that's going to be the answer. You probably felt this when you go into an elevator. Well, this one's accelerating at a much faster rate than you'd ever expect an elevator to accelerate. But when you go into an elevator that's going down, you sort of feel like, I don't know, like it sort of just makes your stomach jump up into you just a little bit. All right, that's because you're accelerating downward, and it's for a brief moment in time. As you're accelerating downward, you're actually lighter. The force on you is lighter than your weight. All right, that's why you have that sensation in a very fast elevator. Okay, let's try this one. This one's a little more complicated. It's going to require you to think about your force vectors and require you to solve for your force vectors in 2 or 3 dimensions. Let me write down something first. You know, we say that the sum of the forces is equal to the mass times the acceleration. We can also say that the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. The sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. And we can also say the same for the z direction, but we're not going to deal with the z direction. So I can break down Newton's second law not only into just this, but I can break it down into the x and y components. And the sum of the forces in the x will always equal max. The sum of the forces in the y will always equal may. We'll get into some more complicated problems, but this is sort of the beginning of that. Because here I have forces that are acting not along the x or the y axes, but on both. And so my first step is I'll draw my force vectors. I have a force vector here, and I have a force vector here. I'll call this FTL, and I'll call this FTR. And then I have another force. What is that force? I have the gravitational force, which is the weight. This is FW. It's going to equal to 23 times 10, or 230 newtons. So now I want to know, what is the tension in the rope on the right? What you'll want to do here is you'll want to break these vectors into their x and their y components. So that's going to be your first step, is you'll find out what is this component in the x direction and what is it in the y direction. And you have to do some geometry, gymnastics, to figure out what are those components. And then you'll want to say the sum of the forces in the y direction is equal to may, and solve then for the force tension in the rightmost rope. We can give you a couple minutes on this, then I'll jump in there. Let you make a little headway on your own first. In just a minute, I'm going to jump in there and help you. All right. This is something called a free body diagram. And in a free body diagram, I'm going to take my object that I'm concerned about and collapse it to a point. I'm going to draw all the force vectors. So it's going to look a lot like what I've drawn here, but it'll help us in the future to think about more complex problems. So my free body diagram will have a force here. It's 230 newtons. And then it's going to have forces here, FTL, and FTR. Now, I need to know what these angles are. And some of you have probably already figured that out. What are those angles? They're what? They're 50 degrees, right. So these are 50 degrees. Let me remind you a little bit of your high school geometry when you weren't throwing D-cell batteries at the teacher, right? If I have two lines like this angle is equal to this angle. And notice that's what I have here. This angle is equal to that angle. So, this is called a free body diagram. You want to find your x and y components. What is the x component of FTL? Right. It's going to be the force times the cosine of 50. So I'm going to write it on this diagram, but I can write FTL cosine of 50. And then similarly, I can write FTL sine of 50. That's my y component of that force. Y'all with me? Nothing new here yet, except the free body diagram is a little new. Now I can do a similar thing with FTR. Here, this is FTR cosine of 50. And then up here, I have FTR sine of 50. Okay? You with me so far? I'm going to let you go. I want you to finish this, but let me give you a little direction. Sum of the forces in the y direction is equal to MAY. The sum of the forces in the x direction is equal to MAX. What is the acceleration of this object? No, it's not negative anything. What is the acceleration? How is this object moving? I know what you're thinking. All right, but that's not. All right. What is this object doing? What's its state of motion? What's it doing? It's zero. It's sitting still. It's something we call a static problem, where it's not moving at all. If you go into engineering at all, right, you take a whole class on statics, which I know none of you are engineers, but if you did, you take a whole course just on statics. That means a whole course about things that just sit still. Because engineers, they build a lot of things that sit still. Buildings, bridges, all those things sit still. And so I have an acceleration in the x direction that's equal to 0, and an acceleration in the y direction that's also equal to 0. So let me show you in the x direction how this would work. I would say the sum of the forces in the x direction is going to be FTR cosine 50 minus FTL cosine 50, and then that would equal to 0. Now that doesn't really help us find FTR or FTL. What I want you to do is to look at the sum of the forces in the y direction and see if you can solve then for FTR. All right, I'll go about 15 more seconds. I'll go on up to 8:15. $8:15? Just guess if you're not sure. Let's see, we're a little bit split. That's okay, this is sort of your first time to do these problems. Let's take a look and see what the answer is. So what we're going to do is we will take a look at the sum of the forces in the y direction. Say the sum of the forces in the y direction is FTR sine 50 plus FTL sine 50, because they're both positive. And then what is the 230? Is it positive or negative? It's minus 230 because it's downward, and so that's a negative value. And this is going to equal to the mass times the acceleration in the y direction, but the acceleration in the y direction is equal to 0. Okay? So now I want to solve for FTR. But what can you tell me about the difference between FTR and FTL? How do these two compare? Is FTR bigger, smaller, or the same as FTL? It's going to be the same. Because those angles are the same, they're going to share the load equally. We can see that in this FTX expression. FTR and cosine 50 minus FTL cosine 50 is equal to 0. That means that FTR is equal to FTL. The cosine 50, if you take the FTL over, it'll cancel out. So I'm just going to get rid of the R and the L because they're the same, and I'll just call it FT. By the way, you have a homework problem that's very similar to this, except the angles aren't the same, and it makes it a bit more complicated to find the force in the tension of the force tension in the rope. But this becomes 2FT sine of 50 equals 230. I just took the 230 over, divide both sides by 2 sine 50, and I solve for FT. So 115 divided by sine 50, and I get 150. So A then is the right answer. All right. I know that's sort of a lot to throw at you. We're just seeing Newton's laws. But let's step back through the process that we did when we solved this problem. First thing you do is you'll usually have a picture, or you'll need to draw a picture. So just draw all the forces that are acting on the object. We draw all the forces. I have two tension forces that are going up at an angle of 50 degrees. I need to find out these angles. And then I also have a weight that's acting on the object. Then I draw a free body diagram, in which case I just draw a coordinate system in the pink, and then I draw my vectors in the right way with the right angles in the right directions. Then I find my x and y components of the vectors if I have any that are off axis. This is what I did here, here, and then here. Find your x and y components. Then you apply Newton's second law, where you say the sum of the forces in the x is equal to max, the sum of the forces in the y is equal to may. And that'll generate, in this case, two equations, which you can solve to find your, in this case, FTR or FTL. All right, so in short, 1, draw a picture. 2, draw a free body diagram. 3, resolve your vectors. That means that you find your x and y components. 4, apply Newton's second law. And then from that you get two equations or more sometimes. Sometimes you might get 4 or even more equations. But you solve for your unknown. In every problem that we work that has to do with forces, you'll follow this same procedure. Drawing a picture, drawing a free body diagram. Eventually you'll just be able to combine these because you'll get really good at it, and you don't need to do this separately because they're really very similar. Resolve the vectors, apply the second law, and then solve for the unknown. China? Second angle. Okay.
Why is it minus the force of x and then some of those?
Okay, good question. So she asked, why is this negative, whereas this is positive? Because if we go back and we look at our free body diagram, our FTR cosine 50 was in the positive x direction, and this was in the negative x direction. So you have to make sure you get your signs right. And on these two, they were both in the positive y direction. I got rid of the R and L at the bottom because I figured out that FTR is equal to FTL. That's really stated in this equation. We sort of reasoned it or intuited it. But here it's written here because if I solve this, I get FTR cosine 50 equals FTL cosine 50 these two cancel out, and so FTR is equal to FTL. And since they're identical, I don't need to distinguish between them. Alrighty? Thank you. Listen, we're going to do a lot more difficult problems. I'm not a whole lot more difficult problems, but we'll get into some more two-dimensional problems next time. You're sort of lost right now. That's okay. If you don't want to stay lost for too much longer, we're going to move quickly through this. Not too quick. We'll move through it. Y'all have a great day, okay? Have a good weekend. Hope you enjoy these extra 2 minutes that I'm giving you.